Yes, screen is visible.
Yes, sir.
Okay. Yeah. Now we'll start the topic. Yesterday we discussed about the de Broglie wavelength. According to de Broglie, so matter means like particles also have dual nature. Okay, when particle is moving, it is associated with a wave. Okay, so by using division and Germer experiment, so experimentally, so we can prove that that particles have wave nature. Wave nature. So in this experiment, I will explain briefly again. Okay, so in this experiment, it contains here electron gun. Electron gun will be there. That electron gun contains filament as well as plate. So there is a potential difference between the filament and plate. Okay, so if while varying the potential difference between the filament and plate, so we can change the so number of electrons as well as speed of the electron here. Okay, so that means this is the high intensity and high speed electron beam. High speed electron beam. Okay, that is instant on a nickel plate. What happened? So those electrons are scattered. Okay, scattered, and diffraction will be takes place. Diffraction will be takes place. So that means by using Faraday cylinder here, by using Faraday cylinder, so we can detect those scattered diffracted electrons. Okay, those diffracted electrons here. Okay, here the Faraday cylinder have there is a two layers. So first layer has there is a some negative potential, and the second because of that negative potential, what happened? It prevents the low energy electrons. So what are the low energy electrons means? Here secondary electrons. Those electrons are emitted from nickel plate. Okay, so here high energy beam is instant means, so what happened? This have some energy, so due to that energy may chance to emit the electrons from the nickel plate. Okay, so those electrons we will call it as secondary electrons. Okay, so by using these Faraday cylinder first layer, okay, we can what is that, remove, we can remove the, that means we can stop the secondary electrons. We can stop the secondary electrons. Only high intensity and high energetic electrons uh, reaches to the Faraday cylinder here. Okay, yes, who is that? H8. Okay, now we are going to the here. So only here high intensity, that means primary electrons reaches to the this collector here. Here collector collects the electrons. So because of the what is that collection of the electrons, what happened? So current passing through the galvanometer. Current passing through the galvanometer. Okay, so we can vary the this Faraday cylinder. So 20 degrees to 90 degrees. So we can move in the circular scale here. Okay, so that means in each position we can measure the how much current is passing, how much current is passing. So what we are doing means, here theta is we are taking in x-axis, current is in, we can take the y-axis. So at theta is equal, suppose 20 degrees. So what is the current passing through this? At theta is equal 30 degrees, what is the current? 40, 50, like that. So that means up to 90 degrees we can take the values. Okay, so that means theta is equal 20 to 90, we can take the values here. So here this Faraday cylinder is movable. Okay, we can take the theta value in x-axis, so and current value in y-axis, so we can get the different curves here. See here. Yeah, so curves will be like this. So that curves will be depends on the so applied potential, that potential applied in between the plate and what is that, filament. Okay, if see here, so suppose if you will take 40 volts, potential difference between the filament and plate is 40 volts, so the curve will be like this. So at a particular theta value, so what is the current is like this. If you increase the theta, so current is increases up to particular value and decrease, so and it will reaches like this. Okay, so that means so for different values of the potentials, it will be curve will be different. So if you observe these potentials here, so at a particular potential, what will happen? 44 volts bump will be started. Bump will be started, and at 60 volts, this bump will be minimized. Bump will be minimized. Okay, so at a particular volts, 54 volts bump shows the maximum bump here. Okay, maximum bump. So that means it is like a maxima and minima of the diffraction. So it is maximum and again it will be minimum. So in the diffraction pattern, we will observe maximum and minimum like that. Here at a particular voltage, 54 volts, and so we'll get a curve will be like this. Curve will be like this. So at which value it will be getting the maximum means for a particular value theta is equal to 50 degrees. Theta is equal to 50 degrees. So we will get the maximum value here. So based on that, so we are doing the experimental. Okay, so now we are calculating, that is the what is that according to the theoretical here. So what is the voltage we are applied here? So 54 volts. If you substitute the here lambda equal to 54 volt, so we'll get the some value, lambda value, that lambda equal to 1.67 angstroms. This is the theoretical wavelength value. Okay, so by experiment means according to the X-ray analysis. So Bragg's proposed one law, that is 2d sin theta is equal to n lambda. 2d sin theta is equal to n lambda. Here d is the placing between the nickel crystal planes. So this is the total nickel crystal arrangement. So this is the one plane of the nickel crystal. This is the another plane of the nickel crystal. So distance between those two planes, that equal to d. So that value equal to constant. Okay, so that value equal to 0.91 angstroms. 0.91 angstroms. And what is the theta? What is the theta means? So this is the theta here. So that means the angle between the plane and incident ray. So that is the theta. Theta is equal to 90 minus. So this is the what is that perpendicular line we drawn here. So that means this total angle is 90 degrees. So but this angle is equal to, so this is the scattering angle, we said that. Okay, so scattering angle that equal to 5. Okay, so here that will be that this perpendicular line divided into this 5 equal to 2. That means here what is the value 5 here? So 5 is equal to, so 50 degrees we are taken. So that's why 5 by 2 is equal to 25 degrees. 5 by 2 is equal to 25 degrees. So only this value, same, this value also. So what happened? Theta equal to 90 minus 5 by 2. 90 minus 5 by 2. Okay, so now what is the theta means? So 90 minus 25. 90 minus 25 means we will get 65. Okay, we'll get the 65. Theta equal to 65. Now substitute the theta value in this equation. Here we are taking n equal to 1 because we are taking first order diffraction. Okay, therefore lambda is equal to, so 2d sin theta. So 2 into d means 0.91. Here this is in angstroms. We are converting into meters. So 10 to the power of minus 10 meters into sine 65. If you substitute these all, if you calculate these all values means we can get lambda is equal to 1.65 angstroms. Okay, so this is approximately equal to the theoretical value according to the de Broglie wavelength. So if you substitute the de Broglie wavelength formula, we can get here lambda equal to 1.67. According to the Bragg's law, here lambda is equal to 1.65. Okay, that means experimentally and theoretically lambda value is approximately equal. Hence we can say that so de Broglie concept of matter waves is proved. Okay, this is about the division and germ experiment. Okay, now coming to the Heisenberg Uncertainty Principle. Okay, according to this, it is impossible to measure both the position and momentum of a particle simultaneously. To any desired degree of accuracy. See here, observe this figure here. So we are measuring the, suppose here electron is moving. Okay, so that means if you say the position of the electron, we cannot say the exact position of the electron. We cannot say the momentum. Okay, So that means you cannot say the momentum exactly. Suppose if you, that means if you say the momentum accurately, if you say the momentum of the electron accurately, we cannot say the what is the position. We cannot say the what is the position here. Okay. Yes. Now observe here. So that means if you measure both position and momentum at a time means simultaneously means, so we can get some uncertainty. We can get the some uncertainty. So yes, who is that? Mute yourself. Suppose if you want to measure, so position and momentum at a time, position and momentum at a time means there is a some uncertainty in the in their values, in their measurements, in their measurements. Okay, so what is that uncertainty means? In the position uncertainty, delta x. So momentum uncertainty, delta p. If you measure simultaneously, there is a uncertainty in position and momentum. Okay, so that uncertainty is delta x here, uncertainty is so delta p here. Okay, so what is delta x and delta p means? So we can, I will explain you. So this is about the so uncertainty principle. That means so we can measure either position or momentum at a time. According to the uncertainty principle, we can measure either position or momentum at a time. If you want to measure simultaneously both position and momentum means there is a some uncertainty in both measurements. Okay, so similarly, so that only here in the wave nature it is explained. So here electron will be there. So electron is actually it's like while it's moving, so it's associated with a wave. So that's why, so we cannot say that so in which position it will be there particular so that it will be there here or here. So that means somewhere electron will be present, somewhere electron will be present. We cannot say the exact position of the electron also. Okay, now coming to the so here we are measuring here delta p is the uncertainty in momentum, delta x is the uncertainty in position. Okay, so if you want to measure simultaneously both means there is a uncertainty will be there. So these are the uncertainties of the position and momentum. So according to the Heisenberg principle, Heisenberg uncertainty principle, if you multiply the both uncertainties of the momentum as well as so uncertainty of the position, so that should be greater than h by 4 pi. That uncertainty value is should be greater than the h by 4 pi. Here h is the Planck's constant, so we know that these are the 4 and pi are the constants. Okay, similarly here delta is the uncertainty in measuring the energy and delta t is the uncertainty in measuring the time interval. Okay, so if you multiplication of these two, uncertainty in energy so and uncertainty in time, that should be greater than the h by 4 pi, h by 4 pi. So that means so we cannot say that we cannot say the how much uncertainty in so delta e exactly. So that's why, so what is that yeah, Heisenberg proposed one formula. So that is by using that formula we can calculate the so uncertainty of the energy as well as uncertainty of the time also, time interval also, similarly uncertainty of the position and uncertainty of the momentum. Okay, so by using this formula we can calculate the uncertainty, how much uncertainty happen if you measure so simultaneously both two parameters. So those parameters also what yeah, some pair of parameters are there. So we can define this formula some pair of parameters only, so that those pair of parameters are here, so momentum and position, and similarly energy and time interval, so one more pair of parameters are there. So those are the uncertainty in measuring the angular momentum and uncertainty in measuring the angle. Okay, so angular momentum and so angle, these are the another pair of the parameter. Those are the delta j and so delta theta. So in this case also, so if you multiplication of both two is greater than the h by 4 pi. So by using this formula we can calculate the uncertainty or uncertainty in either position or momentum or energy or time interval. Okay, anything. Okay, so this is about the uncertainty principle. Uncertainty principle here. Okay, so there is a one meme will be there here. So according to that, so he is asking, do you know how fast you are going? So just he said that no, but I know my location. So that means this is one meme on uncertainty principle. Okay. Now, consequence of Heisenberg uncertainty principle. Okay, so that means what we can explain by using uncertainty principle means. So previously I said that so uncertainty in position as well as uncertainty in momentum. So we can explain as well as so along those, so the binding energy of the electron in an atom can be calculated. So binding energy also we can calculate it by using Heisenberg uncertainty principle. So one more is it calculates the radius of Bohr's orbit. So Bohr's orbit means electron is revolving in a particular orbit. Electron is revolving in a particular orbit. So by using this uncertainty principle, we can calculate the what is the radius of the Bohr's orbit also we can calculate. So this is about the Heisenberg uncertainty principle. Yeah. So now coming to the Bohr's interpretation of the wave function. Bohr's interpretation of the Born's interpretation of the wave function. Okay. So that means actually de Broglie proposed matter wave. De Broglie proposed that matter wave. That means if particle is moving with a velocity, it associated with a matter wave. So that means if wave will be there, means for explaining the wave, so there is some function is required. So for explaining the wave position or momentum or anything, so one wave function is required. So Born's interpreted that one wave function, that is the psi. Okay, so here for explaining the motion or position or phase, anything, so that means we require one wave function. So Born's interpreted the one wave function, so that is the psi here. Okay, now so according to the Born's interpretation, so the wave function psi has no direct physical meaning. It is a complex quantity representing the variation of matter wave. So it is a complex quantity and it represents the variation of matter wave. It connects the particle nature and its associated wave nature statistically. Okay. So now coming to that means by using this wave function, so we can explain the particle nature as well as wave nature of the particle. Okay. The wave function is used to identify the state of a particle in atomic structure. So that means suppose if you will take one atom, so in that atom, so electron is revolving around the nucleus. So in which position it is revolving? So what is the energy state of the electron? So by using wave function, we can identify that. Okay. So now here there is a psi star. Psi star means here psi is the wave function. So here psi star is the complex conjugate of the wave function. Okay. So in matrix you will get what is the complex conjugate. So in mathematics, matrix topics will be there. In that matrix, so what is the complex conjugate? They will explain you. Okay, here psi is the wave function. Psi star is the complex conjugate of the wave function. If you multiply with so directly we can get. Otherwise, we can write this psi star psi det square. So that means here, so we cannot take the negative values. Psi star means we can write det square. Okay, so is the probability density function. Suppose so one particle is moving inside the atom. So what is the probability of finding the particle? Inside the atom means, so by using wave function we can explain. So that means if you will take psi star, that gives the probability density. So how much probability is there? So how much probability is there? So particular atom. Yeah. See here, psi star dx dy dz. So these are the x coordinate, y coordinate, z coordinates. So if you multiply with the, so that means it gives the multiplication of these dx dy dz gives the so volume, a particular volume. So that means if you give only dx, if you will take only dx means that gives the position. That gives the position. If you will take dx dy means it gives the area. It gives the area. So if you will take so 3 dimension, so only single dimension, 1 dimension means if you will take only dx, so 2 dimension means we will take dx dy. So if you will take 3 dimension, 3 dimensional means we will take dx dy dz. This gives the volume. This gives the volume of the system. If what we are taking, so it gives the probability of finding the particle in the region. In the region, so in the region, which region means, so we are taking particular region x and x plus dx, so y and y plus dy, so z and z plus dz. If you will take particular parameters, so you will take so particular region like this, particular region like this. In that particular region, so what is the probability of finding the particle means, so psi star into dx dy dz. So that is the so here psi star means it gives the probability density. Probability density. So total probability means so psi star into dx dy dz. So this is the probability of finding the particle. Probability of finding the particle. So yeah, now if you want to find the total probability means so psi star. Otherwise, instead of psi star, we can write so that psi square. Okay. So that's psi square into dx dy dz. So we are integrating. Integrating means so we are taking total function, total system. We are integrating. So here parameter, so minus infinity to infinity. Otherwise, so we exactly, if you know the parameter, so this position is from 0 to a. 0 to a means we can take 0 to a also here. So we don't know here particular parameter we cannot define now. So that's why minus infinity to infinity. So here we are taking 3 dimension. That's why, so according to the x-axis we will integrate, according to the y-axis we will integrate, according to the z-axis we will integrate. So if you will take the 3 dimension means, so that probability, total probability of the system. Total probability of the system. So what is the so equation for finding the total probability means, so this is the equation for finding the total probability. Okay, this gives the probability of finding the particle in the space or region. So that means this is the total probability. This is the total probability. So what is the total probability? What is the total probability means? So 1. So that means if particle is finding, so that means we can find the particle anywhere. So if you will take the total probability means we can find the particle anywhere. So that's why total probability means we can take 1. Total probability means we can take 1. Okay, suppose what is the exact meaning of probability means, suppose if you toss the coin, so we cannot say that that is head or tail. We cannot say that is head or tail. So what is the probability of head? So there is a 50% probability of head. That means that probability of head is 0.5. 0.5. So what is the probability of tail? So 0. So what is the probability of tail means, that also 50%. That means so what is the probability means 0.5. Tail for tail also 0.5. So total probability means either head or either head or tail. Okay. So total probability is 1. Like that. So total probability of finding the particle. Total probability of finding the particle. So in the region means, so we can take here so integration of total system. Integration of total system. Okay. So total probability equal to 1. Total probability equal to the 1. So that condition we will call it as normalization condition. Normalization condition here. See here. So this condition. So total probability of the system equal to 1. Total probability of the system equal to 1 here. So that condition we will take, so normalization condition. Normalization condition. Okay. So that means what it explains means, so the particle exists in the space. It can be, okay. So what it explains means, so the particle exists in the space. Okay, so that means if you will take total probability means that is equal to 1. That condition we will call it as normalization condition. Here we are taking 3 dimension. That's why this is the volume element. Dx dy dz is the volume element. Yeah. Now the particle is contained only xy plane. xy plane, that is two dimension. So only then the probability of finding the particle is here. So minus infinity to infinity here. So that means according to the x-axis integration, according to the y-axis integration. So here we are taking dx dy, only dx dy. So now total probability equal to 1. Total probability equal to 1. If the particle is confined on x-axis only, that means that particle is moving only along the x-axis, the probability of finding the particle, is, so only according to the x-axis we are integrating here. So that probability function is psi x whole square into dx. Okay, so integration is minus infinity to infinity. So total probability equal to 1. Okay, so that means according to the 1 dimension, 2 dimension, 3 dimension, we can define 3 different equations. So that those are the normalization conditions. The wave function are complex displacement. Psi is complex quantity and we cannot measure it. Okay. Now coming to the, so there is some limitations of wave function. Okay, for explaining the, so yeah, there are certain limitations of wave function as a solution for Schrodinger wave equation. Okay, for explaining the Schrodinger wave equation, so he proposed some limitations for wave function. What is that limitations means? Psi must be finite. For all values of x. Okay, so it should be some finite value. Psi must be some finite value. Okay, whatever we are taking the x value, it should be some finite. Next, second one is the psi must be single value. If you will take a particular x value, so only one value of psi should be there. Okay, psi must be single value. That means for each set of x, y, z, psi must have only one value. Third one, psi must be continuous in all regions except where the potential energy is infinite. So I will explain this condition in potential in 1D box. So that means, what is that means? If you will take atom, inside the atom, what happen? Electron will be revolved. It will move inside. So, but it will not cross the boundary. So, if you give the external energy, then only it will cross the atom. That means that boundary will act as a potential. That means psi must be continuous inside. Okay. So, at the potential, high energy potential, so it will be, so that means for infinite potential it not continuous. Okay, now next one, psi is analytical. That means it possesses continuous first order derivative. So if you will differentiate the psi value, with respect to the t or with respect to the x, that differentiation also continues. First order differentiation also continues. So psi is continuous and first order of the psi also continues. So psi vanishes at boundaries. So I explained you what is the boundary means. So what is the boundary also I explained you. Okay, if you will take the atom, so that means that the atom particular position only, that is the boundary. So outside the atom, so there is no existence of the psi. So that means psi vanishes at the boundaries. Okay. So this is about the wave function. Okay. So before next topic is here Schrodinger time independent wave equation. So before going to the Schrodinger time independent wave equation, so we'll solve some problems based on the Heisenberg Uncertainty Principle. Okay. Yeah. See here. Okay. So so write down everyone. An electron is confined to a box of length 10 to the power of minus 8 meters. 10 to the power of minus 8 meters. Calculate the minimum uncertainty in its velocity. Okay, so we are taking here, so there is a one box will be there, so that box length is 10 to the power of minus 8 meters. In that box, electron is moving, so we have to find out, we have to calculate the, so uncertainty in velocity, uncertainty in velocity of the that box. Okay, for that what we are doing means, here for finding the velocity means, so what we need here, momentum. So there is a relation between velocity and momentum. Okay, so that's why we have to find out the, so uncertainty in momentum, uncertainty in momentum. So what is the uncertainty in momentum means, so delta px, delta px. Okay, so that means when it should be minimum, so they ask minimum. So that means delta px will be minimum at, so position will be maximum, position will be maximum. Okay, so position means, when it will be maximum position means, so what is the maximum position means, length of the box, length of the box, that only maximum position, it cannot go more than that. That means that position is, so cannot, should not be more than that. So what is the maximum position means, so here 10 to the power of whatever the length of the box, whatever the length of the box, that only maximum position. Okay, so that's why maximum uncertainty is equal to, so delta x, that equal to 10 to the power of minus 8. That is the, so maximum length of the box. Okay, that what is the minimum means, so if you will take delta x maximum means, that is the minimum momentum, minimum uncertainty in momentum. Okay, now so delta px minimum uncertainty equal to h by delta x maximum uncertainty in position. Okay, now if h value is constant, that value equals 6.63 into 10 to the power of minus 34, and delta x equal 10 to the power of minus 8 meters. Okay, so if you calculate it, 6.63 into 10 to the power of minus 26. Okay, that is uncertainty in momentum, but we need uncertainty in velocity, uncertainty in velocity. Okay, so uncertainty in velocity equal to m into delta v, you can write now. So this position we can write, so m into uncertainty in velocity. Okay, so uncertainty in velocity minimum is equal to, so delta p max, sorry, yeah, delta p minimum by m, delta p minimum by m. Okay, so delta, what is the delta p here, 6.63 into 10 to the power of minus 26. M is the mass of the electron. What is the mass of the electron, 9.11 into 10 to the power of minus 31 kilograms. Okay, so now if we substitute it, we can get some value here. Okay, 7.3 into 10 to the power of 4 meter per second. So what is the velocity of the electron? So that means for calculating the, uncertainty in velocity, for calculating the uncertainty in velocity means 7.3 into 10 to the power of 4 meter per second. So that means this is very large value, very large value. That means we cannot calculate the exact velocity of the electron, exact velocity of the electron. How much error will be takes place means approximately 7.3 into 10 to the power of 4 meter per second. So this much of uncertainty will be takes place. So that also minimum uncertainty, that is minimum uncertainty for calculating the velocity of the electron. Okay, understood everyone? Yeah, so next one, next formula, see that, so that if the uncertainty in the location of a particle is equal to the de Broglie wavelength, de Broglie wavelength. So that means you see here, de Broglie wavelength, then the magnitude of uncertainty in its velocity is equal to the magnitude of the velocity of the particle, magnitude of the velocity of the particle. Okay, so here some condition is given. So based on that, so that based on that condition, so uncertainty in the location, uncertainty in position is equal to the de Broglie wavelength. We have to prove that. Okay, so given what is that, delta x is equal to lambda m. Okay, so but according to the Heisenberg Uncertainty Principle, delta x into delta px is equal to, we are taking here approximately h, actually, so that equal to h by 4 pi, h by 4 pi. So compared to h value, so h value here 6.63 into 10 to the power of minus 34. So compared to h value, so 4 pi value is so that means very high, very high. So that's why, so we can neglect that, we can neglect that. Okay, so that means if you take the 4 pi value also, only this value will change. So approximately its value should be 10 to the power of minus 34 only. Only this value will be changed. That value will be approximately 1. Okay, 1 into 10 to the power of minus 34. So that is not a large change. That's why we are taking delta x into delta px approximately equal to the h we are taking here. Okay, so from this, so we are calculating delta v equal to h by delta x into m. So this is delta p is equal to, so h by delta x na. So but we know that p is equal to m into delta v. So if you bring m this side means this is the equation. Now coming to the h by this is we are taking here, instead of delta x we are taking lambda, h by lambda m, h by lambda m. Okay, so that means here h by lambda m, this position, this equation means, so how we can write this equation means, here p is equal to mv according to that formula. Okay, so but so we can, write here, so we can multiply with here. So that means mv above and below. Okay, so what we will get means here, so we can get, so p by m. Okay, so that then m, so we know that p equal to mv, so mv by, so here otherwise, so directly we can write h by lambda value equal to, we know that what is that h by lambda, p. H by lambda equal to, according to the de Broglie, lambda is equal to h by p, h by p. So instead of h by lambda we are writing here p. Okay, so p is equal to, we know that formula, so mv, if you can, that means mm gets cancelled, so that equal to v, so that means if position equal delta x will become lambda, so what happened, delta v will become velocity, so that means magnitude. Okay, so if you will take uncertainty in location is, we are taking de Broglie wavelength lambda, so what it will become means, so that uncertainty in velocity will become the, so velocity of the particle, uncertainty in, so velocity become the velocity of the particle. So this is the second formula. Okay, so as tomorrow we will discuss about the Schrodinger wave equation. Okay, so first I will take the attendance. Anyone have any doubts? Any doubts here? If anyone have any doubts, you can ask, otherwise you can leave.
Thank